I am one of the customer assurance guys here at Behler-Young, so I may have spoken to some of you. I might not have, but today we're going to get into the light commercial rooftop unit training. This is going to be kind of an overview of our equipment, plus installation issues, startup issues, service issues, and so on. So that being said, we're going to get going here. All right, first thing I want to say, this is a condensed version of what was a 4-hour training prior to COVID. So we're putting a lot of snow in a small bucket. So we're going to cover a lot of material. Before we get started, I want you to take a look at the bottom left hand of your screen. There is I'll give me a little laser pointer here. You got this little microphone looking thing with the red line through it. You want to make sure that you keep that red line through that at all time. That is your microphone. If you open your mic at all, it causes a lot of feedback and it gets really confusing. So I want to ask you to keep your mic closed. If you have a question, go to the center of the screen here where the little chat window is. Click on chat and then select Behler-Young, because that's the host, which is Isaac. The question will go to him. He will call back, or he'll ask me the question at the appropriate opening. Then we're going to have a break in about an hour. I know it sounds like a long time away. But at the time of the break, I will ask you if you have questions. At that time, if you want to just ask yourselves, or there'll be a question session at the end as well. So if you have a question that you really want to ask, you can hit it with the chat. Otherwise, you can wait till the break. But besides that, I ask you to keep your microphones closed. Okay. I am at home today, so you may hear some background noise. Hopefully not, but okay. ASHRAE 90.1-2016. Okay, and just to summarize what this is, back in 2016, when this standard came along, this is an efficiency standard on our blowers. Commercial rooftop units used to all be single speed blowers. Well, since 2016, anything 5 ton and larger under this standard has to have a 2-speed blower. Okay, so what the 2-speed is doing is your circulation fan. So when G is energized by itself, we're going to have 66% full speed. When we go to Y2, cooling stage 2, or heating call, we're going to go to full speed, which is 100%. Okay, so sorry about that. So again, the G call, the circulation fan is 66% full speed, and then the second stage cooling or heating call will be full speed at 100%. This is going to be the case on everything over 5 tons, including air handlers. So the first part we're going to kind of break the unit down into sections. So the first thing we're going to do is we're going to look at the blowers on the smaller units, and then getting into the larger units. So the 3 to 6 ton, which is the 582K, we're going to break those down into one section, and then we're going to jump up to the 580J, which is the 7.5 to 27.5 ton units. Those are primarily the units that we're going to have in the field, the 580J and the 582K. Now the 582, there's a 3 and 4 ton, which still is a single speed blower. So we don't go to the 2-speed until we get to the 5 ton. And then the entire 580J family now does have a 2-speed blower. So you're not going to get away with it. All right, the model number. There's so many options on rooftop units and so many things change that all of that is buried in this model number sometimes. So you call a branch and say, hey, I have a 582JE and I need a blower motor for it. Well, that's not enough number. And I know it stinks every time the branch wants to say, hey, I need the whole product number. But if we could guess wrong. So you need to get this entire 17-digit product number. And just some of the things, for instance, this 13th position here, that is the blower. Is it a medium static? Is it a high static? Is it a low static? And as you're going to see, as in our parts lookup, that makes all the difference in the world of what blower and motor we have. So for instance, here's a motor, standard static. Here's a motor medium static. Here's a motor high static. If we don't have that whole number, we don't know which one you have. And we're going to guess, because if you don't have a number, because we stock the medium static. So we're going to, that's the motor we would select if you don't give us that whole number. Well, maybe it was a special order. So the point is, we need that whole lengthy number, because every number, every digit or letter in that number means something. So we're going to ask, again, when you do call for part, you get this whole darn number. Every letter means something. Okay. So we're going to jump into the blower first on a 582K. These are the small package rooftop units, 3 to 6 ton. They've been out now for a couple of years. Scroll compressor, but the big difference here is this new vane axle indoor fan blower motor. This is a vane axle blower motor. You may have seen it. It's a big blue ring. Let's take a look at it in a minute. But we're going to take a quick look at this unit. First of all, the control box. Now, all the rooftop units basically have the same controls, okay? And that's what we're going to look at. This is the terminal board, the central terminal board right here, okay? That is where connections are made. There's really no logic there. There's really no control there. That's just where the connections are made, all right? Then we have the IGC. That is the gas control board, all right? That's pretty much the same board on all the rooftop units as well. Other than that, we have some contactors, relays, transformer, thing like that, but that's pretty much the heart of these units. All right, so the central terminal board, we're going to take a look at first, okay, as you see here on the left. And again, if you take a close look at this board, there's no logic on there at all. It's a terminal strip. This is a junction point. You can see right here, this is where your thermostat terminals are. Down here, you can see your pressure switches, low pressure, high pressure, low pressure, high pressure, which is a great place to check the switches to see if they're open or closed. Then over here is your smoke detector inputs. All right, so it's a pretty straightforward, simple little device. Again, just to reiterate everything that it does, again, it's just basically a wire nut. So your thermostat connections, your economizer connections, your IGC plugs in here, your smoke detectors over here, your fire alarm, your low pressure switches. Okay, but there's really no logic on that board. There's not really much to fail on it. All right, so between the two units we have, the 3 to 6 ton 582 and then the bigger 7.5 ton 580s. The central terminal board is a little bit different. The one on the left here is for the larger units. The one on the right is for the smaller units. The big difference is on the smaller units, we have this setting right here for the blower motor. This is where we set the static on the blower motor right here. We're going to talk about that in a minute. That's the difference of between the two boards. So the new central terminal board, like I said, is for setting up our static pressure. Now, it's kind of frightening sometimes when you get out to a job site and guys having blower problems, and we said, "Did you set the static?" Well, whatever the factory set it at. That's not a good answer. That doesn't work. The factory doesn't know what your ductwork is, so we have to set this up in the field. And if you're not setting them up, you're going to go back and you're going to have problems. The smarter the equipment gets, the more particular it is. So, if I look at this little chart, this is on every one of these units. And across the top, there's my duct static, 0.2, 0.4, 0.6, 0.8, and so on. All right. So we need to adjust the static. All right. This will be done with this little knob right here and this little switch. So the first thing we need to do is measure our static. Now, I was a service guy for a lot of years, and this was one of those things I always hated doing. Nowadays, it's pretty simple. Everybody's got a digital meter such as this here. So we want to check static. Now, you'll see air balancers punch holes in the side of the unit to check static. That is not an appropriate place. This chart right here is actually out of the installation instructions, and it's going to tell us in the drop where they want us to check the static. So they want us to check the static in the drops, not through the doors. It could be 30% difference. I've seen a test done with it. So we want to get into the drop below the unit and the return below the unit, not into the doors. So we check our supply static. We check our return static. So let's say we got supply static of 0.51. We have a return static of 0.46. We're going to add those two together. All right, 0.97, which is 1 inch. Okay. Don't forget the economizer and the curb adapter. There is a static amount for the economizer and the curb adapter. It'll be in the paperwork. So when you get the economizer, if you look at it, you'll see from the CFM you have. So 2000 CFM, that tells you what the static is. So add the static for the economizer and the curb adapter. Okay, so we just checked our static, and our static was 1 inch of static right here, right? Now, if I look down this 1 inch and say this is a 5-ton unit, so that's a 2000 CFM blower, right? Everybody knows 400 CFM per ton. It gives me this 9 volts DC right here. Hopefully everybody sees that. So I need to set my blower up to 9 volts DC. That'll give me my 2000 CFM at my 1 inch of static. So I take my DC voltmeter here, and on the central terminal board, you'll see that it says VDC. They look like female spade connectors. You put your red probe in the top positive, the black probe in the bottom negative. And then we're going to adjust the switch first, and then this dial till we get 9 volts DC. So the switch is for a range. So position A is 4 to 7.5 volts, B is 6.9 to 8.7, C is 7.7 to 10 volts DC. So we need 9, so that would fall in C. So I'd put this little switch to C. All right. So I flip the switch to C. Then I'm going to turn this dial until I get 9 volts DC on the meter. All right. That motor is now set up. Okay. That is the proper way to set. Now, what happens if you say, well, I don't want to check the static. I'm just going to crank this thing up to 9 volts DC. And let's say you only have 0.4 inches of static. You can see that should only be 7. The higher that DC voltage is, the faster that blower motor runs. So if your static is only 0.4 inches and you set it at 9, you're going to be ramping that motor up too high, and you'll probably be tripping around on overload. Okay, if I don't set the static high enough, I might not have enough airflow. All right, so this is not a step that we can bypass anymore. It's pretty simple, but you have to do it. Okay. There's some dip switches on the central terminal board. Okay, on the single phase unit, there is 7 dip switches here. You can see them here. And this little chart tells us what those switches are for. Basically, you're not going to mess with those switches. But if you replace that board for some reason, you need to make sure you put those switches back where they were. So in our example, we're dealing with a 5-ton unit. So if I look down here, at 5-ton, you can see 5-ton low static, 5-ton medium static, 5-ton high static. So those are 3 different units, and it tells you how those switches are set up. All right, so those switches are specific to the unit. If you change that board, you need to change, put the switches back to where the old board was. Okay. Now we stock in the small unit, we stock the high static unit. All right, in the larger unit, we stock the medium. But on a special order, you may have gotten something different. So now on the 3-phase board, you have this single or 2 little dip switch setting here, right here. And remember I said on the 5-ton and over, we have a 2-speed blower. That dictates what speed the blower will be on low speed. So the factory default will be 66%, both switches on. That's for the low speed, so the G speed, circulation speed. All right, So that's dictated by that switch. Again, factory default on the 5 and 6 ton will be both on 66%. All right. This is an ECM blower motor. What does that mean? It means it has power to it all the time, just like the blower motor in your furnace. There's no contactor. There's always line voltage on the motor. So if you take a look here, right up here is my terminal strip, right? So here's my disconnect. Here's my L1, L2, L3 coming in. There's my main terminal strip in the unit. And if I follow the wires, let's follow black, right to the motor. Yellow, right to the motor. Blue, right to the motor. So obviously that's a 3-phase. Down here is a single phase. It's just black and yellow. Same thing. We have power to this motor all the time. All right. So there should always be power to this motor. Also, there's nothing shutting this power off. So if you have power surges and stuff, that can cause a problem. So wild leg. I want you guys to make a note of this. Now, is everybody familiar with a wild leg? When we're dealing with 3-phase, sometimes we'll have one leg that's 208. It's called a wild leg. So two ground is 208. If you got all 115 or 112 or 119, whatever, we don't have wild leg. But if I have that wild leg, it has to go on L3. If you're dealing with a Bryant rooftop or a Carrier rooftop unit for that matter, if you have a wild leg, it has to go on L3. All right, it's going to be a test on that one later. Okay, so there's power to those motors all the time. So that's pretty easy to check that motor, right? I could check for voltage right here. All right, I can take my voltmeter. Motor's not running. I can go right to the motor and check for line voltage. Right here on a 3-phase, right here on the single phase. All right, now low voltage. So the motor gets line voltage all the time. Then it creates a DC voltage. The motor actually creates a DC voltage, which comes back up this orange wire. See the orange wire right here? To the board. So the 24-volt DC comes back from the motor up this orange wire right here. So this little metal tab right here, that's 24 volts or 10 volts DC. That 10 volts went through these switches here. We set it to 9. And when that blower gets a call, it's going to send the 9 volts back down this pin, down this gray wire, back to the motor to tell the motor to run. All right. So again, we adjusted it and it's going to take that voltage and send it back to the motor, and that tells the motor what speed it's going to be. So I can actually check for that voltage right there. All right. This is the plug. It's in line. It's in the blower compartment. So if you go into the motor, this is the best place to troubleshoot this motor. This is on the motor side. So if I follow these wires, they go right to the motor directly. Take your blower panel off. You get your meter out. You grab this plug. L1, L2, L3. So there's your line voltage, right? Take my meter. Oh, sorry. I'm going to stick my probes in there. L1 to L2, L2 to L3, L3 to L1. I'm going to check for my line voltage. Again, the blue should be the wild leg. Now flip that plug over, and there's orange, white, and gray. Orange is 10 volts coming from the motor. White is common. So orange to white should be 10 volts DC. The motor doesn't have to be running. This power is coming from the motor. So I check. I have 10 volts DC? No. I have line voltage to the motor? Yes. Then I got to look at the motor. I have voltage coming on. I have 10 volts DC on the orange. Then yes, I have power coming back from the motor. Again, I can go right to the terminal board and check it here too. Now, on a call for blower, again, it sends that 9 volts we created back down the gray wire. So then I can go back. I can go back to gray to white here, and I should have 9 volts if the blower is being called for. So again, does the motor create the 10 volt DC, orange to white? If it does, then we check our output on the call. So when we set that 9 volts DC, we're calling for the blower, we should have 9 volts going back. If we have power on that gray lead and the motor fails to operate, then we have to take a look at the motor. Now, I'm going to warn everybody, and again, I want you to listen. That motor has an electrical lockout. If the power is too high at some point, that motor can lock itself out. So you might walk up onto this unit and the motor's not running, and I have my 10 volts DC. I don't have my 9 volts DC or whatever my return voltage is, and the motor's not running. Before you condemn that motor, shut the disconnect off for 3 minutes, all right? Patience. We got a lot of the capacitor to discharge, and then power it back up and see if the motor comes on. It may have locked itself out on over voltage. Okay. This is a bulletin that had come out on these units. This little plug here is this plug right here. Okay. And what happened is somebody takes their big old honking leads from their meter and shoved them in the front of this plug, and look what happens. So they created a problem. Do not put your meter leads in the front of that plug. Put them in the back of the plug. See what we're doing here? We're in the back of that plug, not in the front. Okay, because we're not going to damage those leads. Where in this picture here, this unit actually came back like this. This was causing the field. Now, because this motor has power to it all the time, if you have high voltage, now, and I've seen high voltage, this unit is designed for 187 to 253. It's 230 plus or minus 10%. I've been in areas where I've seen 255 at times, 256. If we have high voltage like that, we need to put some type of surge protection, phase protection on these motors. But to just simply put it on the unit, it'll keep the compressor from coming on. It's not going to protect this motor. So to protect the motor, we need to put a contactor in line so that if this phase voltage monitor trips, it kills power to the whole unit or to the motor to protect it. Okay, so that's the little Axion blower. Like I said, it's pretty simple to troubleshoot. You just have to know what you're looking for. Setup is really important, guys. I can't stress that enough. So now we're going to look at the 580J. These are the larger units, belt drive. These all are two-speed now, again by code. So let's take a look at the control panel on that one. There's the older IGC. You can see it no longer, it does not have that setup on it. Okay. So how do we do two-speed on these units? Now, we don't use a two-speed blower motor. Generally, these motors are much too big. So we're going to go to we've added what's called a fan relay board. We're going to look at that in a minute. A VFD, variable frequency drive. These aren't scary, guys. Again, once you understand what they're doing, just like the old ignition modules, right? They kind of freaked us out at first, but we got used to them. And then the indoor blower motor. Now, this motor is specifically designed for a VFD. So don't run to Granger and pick up a replacement motor. It has to be rated for use with a VFD. So just be aware of that. So first of all, the fan speed relay board, this is it. You'll see this little thing in there. It's about 4 inches by 4 inches. Okay, and to me, it's easier myself if I understand how something works as opposed to trying to remember, what this thing, right? So I'm going to try to explain how this thing works, what it does. Hopefully this makes it a little easier to remember and a little easier to think how to troubleshoot it. So there's 4 relays, 1, 2, 3, 4. And here they are, K1, K2, K3, K4. Here's the contacts, normally closed, normally open, 1, 2, 3, 4. Okay, so there's my common 24 volts. And let's say I have a call for W1. Now, if you're paying attention, I said W1, heat will always be high speed. So on a call for W1, we energize the K1 relay. All right, the energize would be this relay here. So the little relay pulls in, this contact closes. Now, this 24 volts is DC coming from the drive, but let's see what happens. This goes here, through there, and we energize the high speed. This is the high speed relay. We energize the high speed at the VFD. So there you see it. That energizes, this closes. we send power to the VFD. Terminal 15 tells the VFD to go to high speed. Okay. Now these are relays. How do you check a relay? With an ohm meter. It's pretty straightforward. Okay. Now let's take a look at the VFDs. Now we only use two different versions of the Allen Bradley VFD, the ACS 320 and the ACH 550. This one on the left is a little bit smaller than the one on the right. I have had them substitute one for the other. But let's take a look at, wow, look at all those terminals. Holy cow, what's all that? Don't worry about that. We don't need to worry about that. Right here, look at main. L1, L2, L3. There's line voltage in, line voltage to motor. You see all these terminals, but we're only using these up here. All right, it's pretty simple. 24 volts. The VFD creates 24 volts DC, not AC like your transformer, but DC. So between here and here, your ground is 24 volts DC. So what does it do with the 24 volts DC? It sends it down this pink wire. Now, if you look, all the wires here, but this pink wire goes here, it jumps to terminal 15 and it jumps to terminal 12. Okay, so what happens is the pink wire sends the 24 volts, which should be right here, through this little relay, back through the relay, up the white wire to terminal 15. So it'll go through the relay, back, on this one it's terminal 14, or terminal 14, but it comes back up to DI3, which white is high speed, yellow is low speed. Okay, so one relay sends this 24 volts to the yellow, the other one sends it to the white. Low speed yellow, high speed white. The other VFD, you can see it's wired a little, virtually the same, but instead of inputs 13 and 14, it's 14 and 15. So how would I troubleshoot this? Well, my blower's not running. All right, so first of all, do I have incoming line power? Yes. Do I have outgoing line power? No. Do I have a fault light? No. So let's check for voltage. So again, when this 24 volts DC comes to this input or this input, it's going to turn the blower on. So let's take my DC voltmeter, check from here to here. Do I have voltage? Yes, that means it's not calling, right? Because if this is closed, I wouldn't have voltage. Then I'm going to check from here to here. Do I have voltage? No. So that means this one's closed. So I should have blower running. Now I could also go to ground. So we just check. Do I have power on either one of these inputs here? If I do, the blower should be running. Pretty much, don't know how much simpler that can be. Okay, or if you're not really sure, you could even jump from the pink to the yellow or white, and it should turn it on. All right, so that should make great sense. If you're all sitting next to me, you'd all be yelling, oh, that's easy, right? Okay, so that's what the drive does. And it's pretty simple. Now you see a bundle of wires, but actually there's two blues, which are jumpers, and then the three pinks, and then the yellow and white. Yellow low speed, white high speed. Okay, so this is the VFD right over here. This is the terminal board we just looked at, the fan relay board. This is all pretty straightforward. So here's that. Let's zoom in on this thing for a second. Here's that pink wire. So that's 24 volts DC, which goes into the relay board. Now, if high speed calls, that relay sends 24 volt DC back down the white to terminal 14, tells the VFD to turn the blower on. So again, I can simply check that. If we're calling for low speed, pink goes through, relay energizes, sends it back out in the yellow, and that energizes terminal 13. It turns on low speed. I don't know how much easier that is. I can check from pink to yellow, pink to white to see if I should have the blower on. And if not, then the problem's at the drive. If I'm not calling here, if pink to white and pink to yellow are open, then that obviously means we're not calling for anything. So then I can either look here, or don't forget, sometimes it's best to go back to simple stuff. right? Sometimes when we're not calling for blowers and sometimes when I'm talking to guys on the phone, you always forget. Let's go back to G. Are we calling for the blower? All right, so we always want to dive into this VFD because we think, oh, that's got to be the problem. All right, so what a VFD does is it takes our AC voltage, turns it to DC voltage, we turn it back to AC, but we control the hertz, right, the speed. Because coming out of Edison, everything's 60 hertz. And that dictates fan speed. So what we're going to do is VFD allows us to change the hertz. All right, we can raise and lower the hertz, raise or lower the fan speed. Now, the VFD is capable of a lot of different things. We're only doing 2-speed with this. Now, you may work on some big rooftop units where we do full variable speed. We're not doing that. This unit's not designed for that. This unit's designed for 2-speed. So G, circulation fan, and first stage cooling, we're going to send 40 hertz to the blower. It should run at about 66% speed. Y2 or W1, we're going to full speed, 60 hertz. That's all that drive is doing, all right? So the VFD is used to switch the indoor unit fan motor between high and low speed. High speed, 60 hertz, low speed, 40 hertz. Again, the VFD can do a lot more than that. This unit is not designed for it. Don't overthink it. This is really pretty simple. All right. Air balancer. Yeah.
Quick question. For the VFD, what AC voltage powers it?
Whatever the unit is, either 230 or 460. It depends on whatever the unit is. So if it's a 230 volt unit, we have 230 going to the VFD. All right. If it's a 460 unit, we have 460 going to the VFD. Same thing though, if you have a wild leg L3, it has to be on L3. Okay, so again, all the rooftop units have a voltage plus or minus 10%. So the 230 volt unit is good for 187 to 253. We start getting above 253, we can cause issues. So again, they got to keep that in mind. You know, nowadays with all the electronics, things are a little bit more specific. So let's go back to this for a second here. So the input to the VFD down here, that's line voltage, L1, L2, L3. And then it goes through the drive, and when it calls for motor, it's going to sell L1, L2, L3 out to the motor. Okay, that is an AC voltage coming out of the motor technically. We're changing the hertz. Okay, so but I can check to see if I have output to the motor. It might not be a full 230. It might be 190. It depends on what the drive's going to do, but do I have power going to the motor? Okay. All right. Static. Now, there's a reason these don't, you're going to see the keypad in a minute. The reason these don't come with keypad is because Bryant doesn't want you messing with the setup in the drive. And on variable speed equipment, they'll actually use the drive and adjust the blower to static. That's not what we're going to do. We're adjusting a static pressure like we always have, or like you always hopefully have, by adjusting the pulley, all right? Not by screwing with the drive. So there's a red and yellow, or a yellow and white wire in there. You're going to jump them together. You're going to put energized G, check your static, and then you can adjust your pulley or sheave like you always have. That's how you adjust static on these, not through the drive. All right. Before I move on, though, I want to tell you one thing real critical on both of these motors, the Axion on the little one and the VFD on the big one. They will, everybody listen really close, they will run in the correct direction no matter what. All right? If I swap a leg of L1, L2 on a 3-phase, the blower will still run in the right direction. So you cannot check blower or compressor rotation by looking at the blower. Okay, I want to be real clear. You cannot check compressor rotation by looking at the blower. The blower will run in the correct direction no matter what. So you have to put a gauge on the compressors to make sure they're running in the right direction. All right, so I want to make sure everybody's really clear on that. Okay, so here's the keypad. If you get a replacement drive, get a lightning strike, takes the drive out. The new drive will come with the keypad because we have to configure it. It's really pretty easy. You tie into it, give me a holler. I'll walk you through it if you're not comfortable with it. If I have time yet, we can sometimes even set them up for you in a branch and then send it out to you. Okay, so this keypad will come on it. It'll say, do you want to use startup assist? The answer is no, because that'll just mess us up. All right. So the drive will also come with this book, and this is going to tell us our parameters. This is pretty straightforward. So I need the blower, motor, and drive part number. So right here is the number for the drive. So you look on the drive, you look at the Bryant part number, you look at the blower motor, look at the part number, you find them on this little chart. Right across the line is my parameters. So first thing, voltage, amperage, hertz, RPM. So I just have to go through step by step to each one of these sections, 9905, 9906, and enter this information. This will take you all of about 2 or 3 minutes. Again, you're not comfortable, give me a holler, we'll walk you through it. Or like I said, if you got time for the branch to ship to me first, I can program it for you and then send it out to you. Now the new units, you'll see this tag right here. See this tag in on the door here. I lost where'd my little pointer go here? There it is. This little tag right here in red circle, that's all the parameters. So 9902, 9905, 9906, and all that information. This all has to be set up. If you put a replacement drive in that unit and do not configure it, the blower is going to run at 6%. I don't know where that number comes from, but the blower is barely going to run. You're going to see the pulley going like this. So if you're changing drives, it has to be programmed. It has to be configured. It won't run without it. Okay, so the newer units after like mid-early 2020, this tag started appearing on the unit. So I don't have to look it up. Can't stress enough, do not use start assist. This tag is actually in the unit to remind you not to use start assist. Okay, because that could cause us other issues that we don't want. Okay, so yeah, do not use start assist. So I want to look at this for a second here. So we find the drive, we find the blower. And if you look down this list here, this is all pretty common sense. 460, so if it's a 460 volt unit, set it. Nominal amps, 4. Motor hertz, 60. RPM is pretty self-explanatory, nominal horsepower. Now, this nominal horsepower, the motor, this is nominal, it's not horsepower. They're 2 different ratings. So constant speed, 1 low is 40 hertz, constant speed 2 is 60 hertz. These are both set low from the factory. And then max amps, this is a really important one because if the unit's drawing more than what this max amps are set at, the motor's not going to run at full speed either. Okay. Minimum frequency, 0. If that's anything else but 0, that means the drive won't shut the blower off completely. And so on. So just basically follow those. Now this motor, just like the small units, gets power, and the drive gets power 24 hours a day, 7 days a week. There is no contactor in here for the blower anymore. Okay, if I look inside this control box, there's no blower contactor in there anymore. All right, that blower, motor, and VFD gets power all the time. All right, it's always powered. All right, so here's a picture of the drive tucked away behind the unit or inside the unit. In the event you lose a VFD, right? So you're checking, I have line voltage in. I have a call on yellow for blower, right? So I've got, it's closed from pink to yellow. I've got a call. The blower's not running. So I check, I have my 230 input voltage. I have no output voltage. So I determine the drive is bad. Now, the drive, like I said, you're going to have to call and get it from us. Then you're going to have to program it. Well, in the meantime, this was kind of nice, is if you look right here, you can see spade connectors. So there's my yellow, black, blue, L1, L2, L3. They're spade connectors. That goes up to the drive. And then coming out of the drive, they're spade connectors again. And then going to the blower motor. So I can simply unplug the drive and plug the motor in directly. So now if I look over here, you can see this is, the left side is coming from the disconnect. Right side is going directly to the motor. So I can simply bypass that drive if I need to. Now, if you do this, remember there's no contactors. So that blower is going to run nonstop 7 days a week until you get back there with the VFD. But in a pinch, I can simply bypass the VFD to get the motor running. Okay. If you lose a drive, make sure you ohm out the motor as well, because the motor, if you know, three-phase motor should have consistent readings. If the readings are not the same, then the motor itself could be what took the drive out. Normally it's voltage, power surges, and such things. Okay, so again, check your voltage. Back used to be meaning checking your voltage meant, hey, do I have voltage? Yes. No, nowadays we actually have to check it with all these electronics. Plus or minus 10%. So 230, we got 187 to 253. You know, you're working some area in your 255. Ooh, that voltage is beyond the limits of that unit. And we could have problems. Power surges, we can have problems. So phase monitors, surge protectors, things like that. But again, that unit, that drive gets power all the time. So if you're going to put a phase monitor, voltage monitor, you're going to want to add a contactor to kill power to the drive. All right. On units equipped with a VFD, the indoor fan motor rotation cannot be used to check compressor rotation. Again, the blower is running the correct direction no matter what. So if the blower is running the right direction, don't assume the compressors are. I know it's 12 degrees right now with 2.5 feet of snow, and you're starting a rooftop unit today, and you don't really want to turn the compressors on. Well, the only way to check this compressor rotation is by turning them on. Put a gauge on them, check rotation. Your suction pressure should fall, head pressure should climb, and they shouldn't make a lot of noise. But it's the only way you can do it. So you start it up, the blower's running right way no matter what. Throw a gauge on, check the compressor rotation, it's good. If the compressor rotation is bad, just change the L1, L2 at the unit coming in. Because again, the blower will run the right direction no matter what. So you'll change power coming in like you always have. But remember, wild leg on L3. So if you got wild leg on L3, the compressor's running backwards, swap L1 and L2. Okay, I have had somebody change the compressor on a brand new unit because they wouldn't pump, and it was simply, they were running backwards. Well, they thought the blower was running the correct way, so the compressors must be bad. No, the blower will run the correct way. No matter what you do, it will run correct. All right, so visually confirm the indoor fan motor rotation is correct. Again, it should always be correct. If the fan motor is running backwards, now if somebody changes the drive and they don't wire it back in the same way they disconnected it, then the motor could be running backwards. So if you do have a motor running backwards, then you're going to swap the, double check the wiring to and from the drive to make sure it is as it was from the factory. So look at the diagram, make sure yellow's in the right spot, black's in the right spot, blue's in the right spot on both in and out of the drive. Because if you reverse one of those coming out of the drive, that will reverse the motor. All right, make sense? Okay. Belt tension. Now, this is the one we get lots of calls. You got the jobs, and sometimes the belt is so loose you can take it off by hand. You don't even need it. You know, you can grab a hold of it and almost pull it off. A lot of things go into causing this, I think. First of all, I still hear guys say, well, it's set from the factory. This unit has traveled a long way since it left the factory. All right, I know we treat everything with kid gloves on our trucks, and I'm sure the freight companies do as well. So even all that said, these belts are loose and they need to be adjusted. Our static is not factory set. We need to adjust the static. So when we get calls out, we go out to a job and the belts are damn near falling off and the thing's tripping on limit. Guys, this is part of your startup. You have to do this. These are not set these units and run out the door. We need to check this. Now, this belt tension is one it comes up a lot. And so I want to talk about it for a second. This here, I remember this from when I went to community college 150 years ago. And we always talked, remember the deflection on the belt, 1/2 inch, 3/4 of an inch, 1 inch. All right, everybody remember that? That was for sleeve bearings. All right, sleeve bearings were a brass sleeve that the shaft runs in. So back when you see this crap here, this is sleeve bearings, okay? This is not what we're dealing with. So do not look for that 1/2 inch or 3/4 or worse, 1 inch of deflection in that belt. That belt is way too loose. It's gonna slip. We're never gonna get full speed. Okay, we had our expo several years ago in Novi at the Expo Center. It's pretty impressive if anybody had been there. But our belt guy, Larry from Best Torque, Larry's really excited about belts. And he has this contraption that you adjust belts and he tells you if the tension's correct. It's actually through a machine with electronics and a computer, all kind of cool stuff. Anyways, at our expo, every contractor that walked by, Larry asked them to adjust this belt and then he tested it. I don't know how many hundreds of contractors we had go through there that day, myself included. Out of the hundreds, 5 people got that tension correct. I was way loose. I thought it was too tight. So don't be afraid to tighten these belts. All right, this picture here that you're seeing, this is wrong. Wrong. Okay, that's way too loose. And like I said, out of those hundreds of contractors, and this at Expo, so it's mostly the owners and bosses, out of hundreds of them, 5 of them got the tension correct. All right, so don't cause yourself problems by not tensioning these belts properly. Okay, there is a special tool for tensioning belts. Okay, this little picture down here on the right. All right, I have not seen a digital version. This is pretty simple, pretty inexpensive, but we need to properly tension these belts to get the proper airflow. Also, the belts will last a lot longer if they're tight enough. So this little chart here is out of the installation manual. Now, if you have clean knees, it means you're not reading the installation manuals. All right, read the manual, or at least pictures. Wherever there's a picture like this, stop and read it. So this is the drive pellet pulley. This is the motor pulley. And what they're going to have us do is measure the span between the drive pulley center and the blower pulley center. Okay, now, and then measure our sheave. So smallest sheave diameter. So that would be the motor drive pulley. So let's say it's 3.8, let's say it's 4 inches. Okay, so that would be here. And we're using a brand new notched or cogged belt. So we go over here, notched or cogged belt, new. So 7.4 is the inch pounds of tension on that belt. So what that means is I'm going to take this little tool here. I'm going to push it down on the belt, put a straight edge here. And that's the deflection I should have on this gauge. The 7.4 is the tension. And guess what? That belt is going to be like tight. It's not going to be, it sure as heck's not going to be this. Not even going to be close. All right. So you want to properly tension your belts. You get a hold of this thing. Alignment, obviously you should use a straight edge to get the belts aligned properly. Now, sometimes you get a really thick pulley, you know, use some common sense. You should be doing the edge of the belt if you can. But this tension is huge. And I heard one of my counterparts this week talk to the guy 3 days and finally determined that the belts, you know, they finally got the guy convinced his belts are too loose. The thing's tripping on limit. So this is a huge thing. All right. Static pressure on these belt drive units. Now, standard static, if you look down here, I'm going to zoom in so everybody can see this. Standard static, medium static, high static. This is how a unit is ordered. Now, in the larger units, we typically stock the medium static. Now, what does that mean? It means the static range they can operate under. So the medium static, which is the medium gray here in the middle, if you look at this 5,000 CFM unit, that unit is good for, if I follow this across, 0.8 inches of static. All right, everybody see that? If I have 1 inch of static, I have to go to the high static unit. Now the motor's the only difference. So, if I'm working on a medium static unit, I look on this chart and I have 5,000 CFM and I have 1.2 inches of static, I need to change to the high static drive motor. The pulley will not adjust enough. So anyways, let's say I have 0.6 inches of static. I have to adjust it accordingly. I have to adjust my RPM accordingly to get the static I need. So, I have to adjust that belt accordingly for the static I have. But again, if I need to get above, in this case, the 0.8 inches, I need to go to the 1 or 1.2 inches. I have to change the drive. So if you're checking temperature rise or you're checking temperature split, this was always an easy cheat we always did. And I just don't have enough airflow. And I cranked the thing up and it's cranked in all the way. I don't have enough airflow. Check your static. Take a look at this. Good possibility you need a higher static blower. The pulley's not going to change it. You have to change the motor. So again, you look at the difference here, brake horsepower. So this requires 3.63 horsepower, see right here? But if it's a 1.2 inches of static, it's 4.28 horsepower. So it's a bigger motor. So you can change the pulley all day long. This medium static unit is not going to deliver the right airflow at this higher static. Okay, so now where are we at now here in time? Okay, so all right, so we got a few minutes here. We're going to stop for our quick little break. Actually, I'm going to continue on because we still got about 6 minutes, so I'm running a little early. So we're going to hang on to the break, so just hold that thought. Okay, so there's the blower motors we just looked at. Again, some things I want to reiterate. You have to set the static up on them. If you're driving them on the roof and you're going to run, you're going to be back. Belt tension, simple thing. You got to be doing it correctly. Static pressure, you need to be reading it in the ductwork, not through the doors. I know it's easier through the doors. It's 20 feet in the air. I hear all the reasons, but you can't do it. It doesn't work. The Axion direct drive motors, the 3-phase the wild leg is L3 or blue. The VFD large units, those are all 3-phase. Wild leg has to go on blue. Okay, cut and dry. If there's high voltage, you're going to shut these things down. Okay, so we got to be checking our voltage. That needs to be part of our startup procedure. And if I have 250, you might want to look at putting some type of voltage /phase /surge protection on these units. Okay, to protect the electronics. Okay, so I just can't stress that stuff enough. On the Axion motor, it can electronically lock itself out. So if you are working on that direct drive Axion and the motor's just not running, and I have my 10 volts DC, I have my 9 volts being its calling, or whatever I have it set at. If I'm getting my DC voltage back up to gray wire, it's not running. Before you fault that motor, shut the disconnect off. Wait 3 minutes for the discharge and see if the motor starts again. And if you're running voltage on the high side, or you got this thing ramped up too high, that could be what's locking it out. All right, that unit, that's been around since 2016. So, it's been over 4 years since we've had that blower. And though, there's been some hiccups here and there, for the most part, it's been a good motor and it's running. So we just have to set it up correctly. VFDs, if you have a failure in a VFD, again, check your inputs. Is it calling? Do you have power going to the motor? But if we lost the VFD, check the power and make sure your wild leg is on L3. Ohm out the motor. All right, because if the resistance on all three legs is not consistent, then the motor is the problem, then that caused our drive to go. So just want to, again, reiterate that one. So, okay, so now we're gonna just start in the next section, and then here at a couple minutes, we're gonna take our break, but we still have a lot to cover. So IGC, integrated gas control. So this is the other board, all right? We have the terminal board, which is basically a junction point, and then we have the gas control board. This board here has not changed much over the years. There's a fuse on it. There's a light we're going to talk about in a minute. This handles ignition. It handles flame proving, flame monitoring. This is what these two relays here are: your high and low speed blower. This is what turns the blower on for heating and cooling. So this is what's sending the signal to that little fan relay board that's coming off the IGC. All right. This little jumper over here, you all see, that is delay off for air conditioning. All right. There is no way for you to adjust the blower on and off speed for heating. Okay. That we cannot do that. This little jumper is for cooling only. Has nothing to do with heating. All right. The 24 volts comes directly to this board first and through this little fuse. So if the whole unit appears to be dead, let's take a look at this fuse. Okay. So I just want to give you some heads up on this little board here. And for the most part, this is the same board on both units. Okay. Proof of combustion. For years, we used what was called a Hall effect sensor for our inducer. So the inducer came on, we had a Hall effect sensor. Several years ago, we went back to a pressure switch. So the inducer is always going to be the first thing to come on, even on most furnaces. Thermostat calls, inducer comes on. All right. Then we have a pressure switch. We'll talk about the Hall effect sensor because we did use a lot of them as we move on here. So on a call for heat, first thing comes on the inducer, pressure switch makes 0.18 is when it's going to close, the negative 0.18. Okay, that sends a signal to the IGC. The IGC is going to ensure at that point that all the limits are closed, the rollout switch is closed, and that we have no flame signal. So we make sure that all those limits are closed. The inducer comes on, the draft inducer, the draft switch closes, sends a signal back. If it is the old Hall effect sensor, we're going to send a voltage back. We'll talk about that in a minute. The burners will ignite within 5 seconds. So these are direct spark starts, gas valve opens. If they do not light after 22-second delay, or if they do not light after 5 seconds, they shut down. There's a 22-second delay, they'll try again. So again, igniter starts, gas valve opens, 5 seconds, no flame proof, shuts, waits 22 seconds. It's going to try again in 22 seconds. Igniter starts, gas valve opens. And if it ignites after within 5 seconds, we continue. If not, it drops out and waits another 22 seconds. This trial for ignition will repeat 15 minutes or until burner ignites. So it'll continue to retry for 15 minutes and then it will lock out. So if the ignition has not been proved, the heating will then lock out. All right. So the sequence of operation on heating especially, it really eases troubleshooting things. Call, inducer comes on, pressure switch sends a signal to the board times out, opens the gas valve, starts the igniter. If the igniter lights, we send a signal, keep the valve open, and in a certain amount of time, the blower comes on. Igniter doesn't light after 5 seconds. We shut down the ignition attempt, wait 22 seconds, we try it again. After 15 minutes of failure to ignite, it locks out. All right, so if we understand that, it just makes it easier. Okay, so we're a little after 10 now, so we're going to take a 10-minute break, okay? So we still got a lot to do here, so let's see. It is 10:01, so let's be back here at 10:11. Anybody have any questions before we go? Isaac, anything?
Nothing more written outside of the one you already answered, so we should be
Okay.
good.
All right, so like I said, we'll be back here in at 10:11, and we'll get started again.
Perfect. Thanks.
All right, everybody back? Yeah, we're back. We're ready to go. All right. So we just talked about the sequence of operation of the IGC, integrated gas control. Okay, so once ignition is started, we're going to continue to monitor limits. After 45 seconds, the blower will start. Now, again, we can't change that, but it'll adjust itself. We'll talk about that in a minute. On a two-stage unit, the second stage will ignite according to the thermostat. Indoor fan will cycle off 45 seconds after the burner shuts off. Again, that will adjust itself. We can't adjust that. Okay. So there are fault codes on the IGC. So that little LED that's on there, on constant is normal. Off means we probably lost our 24 volts or the fuse is blown. Single flash means that blower time has been altered, meaning it adjusted it itself. So single flash is not a fault. It just means that the blower adjusted itself for heating, either on or off time. We'll talk about that. Two flashes, limit switch fault. Three flashes, flame sense fault. Four flashes, four consecutive limit switches means the limit's tripped 4 times in the same heating cycle and it locked out. 5 flashes, ignition lockout. 6, inducer draft motor fault. 7, rollout switch fault. 8, internal control fault. 9, software lockout. So we'll talk about all these. All right, integrated gas control board with single LED fault display, 100% lockout. Interrupt power to reset fault. So all these will be reset, will clear if we reset power, including this adjustment of the evaporator. So limit reset. Before we move on, I want to talk about this limit here on the 582. This is a picture of that Axion blower motor that we've talked about. And right here on the side is called the stator limit. Now we have our main limit down here. Let me change back to my laser pointer. Down here with the 2 purple wires, that is our main limit. All right, if that trips, that'll show up here. This limit here, and if I zoom in on close here, you can see, you can't see it. There's a red reset button on this limit. It's on a unit that's built before the middle of 2020. This is a manual reset limit. So if this light is out, all right, if this light here is out, like you see right there, check this limit, all right, because if that limit trips, that kills 24 volts to this board if it's the manual reset limit. Now, in I think the 40th week of, or middle of, or late in 2019, that they switched this to an automatic reset limit, which now puts it in series with this limit. Okay, but if there's a manual reset limit, it should still function fine. If it's tripping, there's probably an underlying reason. So, but again, if you have no light here, that's because this limit is probably tripped. This is a bulletin that allows you to change that manual reset limit with an automatic reset limit. And I'm going to warn you, if that limit is tripping, something is wrong. And simply putting the auto reset limit in is not going to correct the problem. We still have to find the problem. Okay, so basically in this bulletin, it tells you that you can replace this relay, or this limit rather, this auto reset limit with this manual reset limit with an auto reset limit. But what they want you to do is these 2 red wires here, those are 24 volts. So they're going to want you to wire nut those 2 wires together and then put the new automatic reset limit in series with this limit. So you'll take this wire off and put it here, and then you'll get a new wire 24 inches long and put between the 2. So they're in series. All right, so that's to eliminate that manual reset limit. All right, so again, tie those together, and then you're going to put the new limit here, and you're going to put it in series with the main limit. And when we get to this in a minute, you'll see why. But I can't stress it. If you got a limit tripping on a 582, just changing that to an auto reset limit's not going to fix the problem. We have to address the problem or it will continue. And we're going to talk about some of the potential problems. All right, so fault one, it's not really a fault. If it's flashing one time, it means the blower time has been altered in heating. So it will alter itself. This is the conditions in which it's altered. Initially, it's 45 seconds. If the limit opens before the blower starts, so burner comes on, and before that 45 seconds, the limit trips. 5 seconds will be deducted from the blower on time. And it'll continue to deduct 5 seconds all the way down to 0. So the blower could start instantly. All right. But for that to occur, the blower has to trip. The limit has to trip before the blower comes on. The off delay, the blower will shut off after the burner shuts off in 45 seconds. If the blower shuts off and the limit trips while the blower's off, then it's going to add 15 seconds to the blower off time. So if 45 seconds, the blower shuts off, and then a couple seconds, the limit trips, the next time the blower will shut off in 60 seconds. And then it'll go to 75 seconds, and then it'll go to 90 seconds, all the way up to 3 minutes. So if you've got that light flashing one time, it just means that this has been altered. This is the only way to adjust the blower time. It's going to adjust itself in the limit trip. Okay. Fault 2, main limit switch open. All right. So the main limit now, that manual reset limit we talked about, if we do follow the bulletin and replace it with the manual reset or with the auto reset limit, it is now going to be in series with this. So it's now going to react the same way instead of killing 24 volts. Gas valve igniter disabled, indoor blower inducer will be energized. So if a limit switch is open, the blower will run continuously. Okay. If limit closes within 5 minutes, the faults will clear. So if the limit closes within 5 minutes, it will clear and will continue our cycle. If the unit still has a heating call, it will start up its startup sequence again. It will reset when the heating call is ended. So if we recycle the thermostat, if we're having limit trips or if we've had a limit trip, first thing, check temperature rise. That's the first giveaway. We're going to talk about that in a second. And then, of course, checking gas pressure. So checking temperature rise, this is a really simple test. Now, back in the day when I started in the industry, this was part of our startup procedure. And for some reason, a lot of new techs don't do this. They haven't been taught to do this. This is a real simple test to see how the unit's doing. Very simple. We're going to read the return air temperature, get the heat running, get it nice and stabilized. We're going to check our return temperature. We're going to check our supply temperature. So in this case, I had a return of 60 degrees, and let's say I have a supply temperature of 100 degrees. So I have a 40-degree temperature rise. Now, if I look on the tag of this unit, this particular unit here, I'm allowed a 20 to 50-degree rise. So if I have a 40-degree rise, that's not bad. It's kind of in the middle there, right? What if I have a 50-degree rise or 60-degree rise? I'm either overfired or I'm not moving enough air. That's the two things, right? Because if my temperature rise is too high, either I'm overfired or I'm not moving enough air. What if my temperature rise is too low? Then I might not be firing high enough. Now, if my temperature rise is too low, that can also be a problem. It's not going to trip the limit, but I'm not going to heat properly. I could condensate really bad. So this little test is really simple and straightforward. Now, I have had guys say, well, at test, I got a 40 to 80 degree allowable temperature rise, and I have a 70-degree rise. Well, the other thing we got to look at is return air temperature. How high is it? Okay. Now, a lot of duct systems, what we do is we use a plenum return. So we got a 20-foot high building, right? And the ceiling's at 8 feet, 10 feet. You got 10, 12 feet above it. And you're using the whole plenum as a return. So you got a little drop out of the bottom of the curb for your return. Okay, something called stratification. All right, and stratification has to do with the denser cold air falling, the warmer, lighter air going up, and in a high ceiling area, or we could have a drastic temperature difference in 15 feet. All right, especially if the unit's been setting off, you go into setback at night. This is why you want to be careful of going to too big a setback. So you go into setback at night, the unit fires up in the morning, and we start to build up all this heat high up in the building, all right? Because we're stratifying. Now, what happens if your return air duct is up here? You're just using a straight drop like this, okay? And you got all this 80, 82 degree air up here because this unit's been running, trying to come back from makeup or from setback. What happens if I got 80, 82 degree air going in this return air here? Because I've stratified. We're going to trip the limit, okay? So even though you don't have a temperature rise higher than you're allowed, if I've got a return air of 80 degrees, 78, 80 degrees or higher, you're going to trip the limit, okay? Stratification is a big cause from that when we're doing, when the drop from the curb is really short, or I've been to ones recently where there's no drop and then the supply ducts are a couple feet below the return. All that heat's just going right up the return. So that's something else we should be checking is that return air temperature. And we start approaching 80 degrees or higher, we have to address that because we're going to trip the limit. Long setbacks, we set it down to 50 degrees at night, 55 degrees at night. You come in this morning, it was 16 degrees last night, right? So that burner comes on and we got to go from 55 all the way to 75. It's going to run 20 degree rise. And during all this long run time, the stratification gets really, really big. All right. So I start to park all this warm air up here. It's really cold down here for being off all night. So I start to stratify really bad. And so even though the space isn't up to temperature, I start getting all this warm air accumulating up above and it hits that return. And we start tripping the limit. So that's something we really got to look for when we're tripping a limit. Stratification, do we have the duct system that's allowing all this heat to build up above? And especially when we've got a very limited drop for my return like this. It drops up in the joist. That's a perfect place for air stratification and tripping limit. So again, put that in your book. If you're getting the 80 degree return air, you're going to cycle on a limit. And here's just another example. If I've got 80 degree return, so when I'm checking my temperature rise, if I have 80 degrees on the return or higher, even 78, 79, you're going to trip the limit. You're stratifying, you got to figure out what to do about it. Maybe you extend this return drop. Maybe you move the registers. Whatever you're going to do, you're going to have to do something about it because if you're in the 80s, it's going to trip. Now, the one I always get is, well, the old unit didn't trip the limit and it did the same thing. Yeah, well, the old unit was 25 years old. The blower came on strictly on time and the limit would trip and reset and trip and reset and we'd cycle on the limit. Well, because of modern codes and energy requirements, these will lock out. If I have 4 consecutive limit trips, I'm going to lock this unit out. So we can't cycle on the limit anymore. I can't tell you how many houses I was in when I was newbie in, 1,200 square foot ranch with 140,000 BTU furnace in it. And they cycled on the limit. The equipment didn't know any better. Nowadays, we do know. And it won't do it. So this is an issue. That temperature, that return temperature is too high. That's an issue. Okay, gas pressure. Gas pressure. Now, this is another one I hear a lot of guys say, well, when that gas valve left the factory, Wright Rogers adjusted it to 3.5 inches, blah, blah, blah. Yeah, they might have. But again, this unit has traveled thousands of miles. The freight company handled it. We handled it. That gas pressure is not in line anymore. And I've seen these things right out of the box with 3.8 gas pressure because those need to be adjusted. All right. You put your manometer on there, you adjust it to the rating plate. Okay. That is something that has to be done. And overfired is going to cause high temp rises, limit trips. So again, limit trips are caused by airflow issues, stratification, or high gas pressure, overfiring. All right, fault number 3, flame sensor fault. Now, a flame sensor, and we're going to talk about this in a second, this is not a thermocouple. This is a piece of steel and with a ceramic insulator. So flame fault means that we sensed a flame when one shouldn't exist. All right, that's probably a crack in the ceramic. A chunk of rust across it's not going to cause a faulty flame. So it means, yeah, we at some point we sensed a flame when one shouldn't have been present. Maybe the gas valve stuck open, so we did have a flame. Okay, but the inducer, the indoor fan and inducer will be on, because if the gas valve were to stick open, the flame would stay on. Of course, it would leave the blower running, so that we would at least not overheat the unit. Okay, normal operation shall resume if fault clears, but fault code will remain. So if this false reading clears, it'll continue to run the unit. Okay, we're going to talk about flame signal in a minute, and we're going to get into that a little bit more. 4 consecutive limit trips. If we trip the limit one time in a cycle, it'll clear. If we trip the limit 4 times in one heating call, we're going to lock the unit out. All right. So again, if I know I'm tripping the limit, if I trip limit 4 times in a heating cycle, the unit's going to lock out. So if I have that Axion blower with the manual reset limit and I put the auto reset limit in it thinking it's going to cure my problems, it's not. We still have to correct that problem. All right, so 4 consecutive limit trips, heat will lock out. This lockout may reset by removing the heating coil. So if you take the heating coil off, turn the temperature down, turn it back up, it will clear. It will also clear after 1 hour. But it's been off for an hour, 16 degrees outside. It's cold, so you're going to get called on this. If this happens, like we just talked about, check your temperature rise, check your gas pressure. Limit trips are due to overfiring, underfiring, not enough airflow. That's generally the things that are causing it. Or stratification, high return air temperature. Okay, fault 5, ignition lockout. Now, flame signal, we're going to talk about for a second, because this is some things, it's actually fairly simple, and a lot of guys don't really understand it. So we're going to talk about this for a second. So ignition lockout. If ignition is unsuccessful for 15 minutes, this lockout will occur. So if I've tried my 5-second ignition periods, 22-second waits in 5 seconds, up to 15 minutes, we're going to lock out. Why did it lock out? Well, did it light? That's the easiest one. The crossover tubes are dirty. So if you look at the burner, you got the crossover tubes. So the main burner's light, first burner's lighting, but it's not carrying it across to the flame sensor. Is the flame sensor bad? Is the flame sensor wire bad? Check the gap in the flame sensor. Is there any rust hanging down on the sensor? Flame signal minimum 0.5 microamps. Now we're going to talk about checking that in a second. But if we have less than 5 microamps of flame signal, well, that won't prove a flame then either. So we need to check that. Check gas valve operation. Maybe the gas valve's not opening, right? The spark's coming on, but we're not opening the gas valve. So the first thing we should do on this is it lighting? If it is lighting, then we got to look at the flame sensor, or maybe the flame, like I said, is not carrying all the way across. If the heating coil is satisfied or power is reset, another ignition sequence will start. So if it locks out, we recycle the power or turn the heating coil off, it'll reset. So let's talk about flame rectification for a minute. This is the rooftop unit with the burners removed. Over here is our flame sensor with the pretty yellow wire. Again, that's not a thermocouple. Guys say, well, it's glowing cherry red. I don't care how hot it is. All right. That's a conductor. We're carrying a low voltage current from the sensor through the flame to ground. All right. That's how that works. Here's my igniter. There's my igniter. Here's my ground. So I make a spark right here. Once it starts sparking, the gas valve opens. This burner lights, hopefully lights this burner, this burner, this burner. Once we carry across, we get a flame established. The flame picks up the current from the flame rod, carries it to the ground. All right. So if that last burner doesn't light, we can't get a flame signal. If this ceramic is cracked, it could be bad. If this wire is bad or shorted or broken, this gap This is the gap between the igniter and the electrode, or the igniter and the ground, right here, side to side and in front of the burner. What happens if that igniter is touching the burner? Well, it can't spark, right? It's short of the ground, so we can't spark. We're not going to ignite. All right. The flame rod, and again, I sound like a broken record here, but the flame rod is not a thermocouple. Heat has nothing to do with it. It's a conductor. It's a contact, if you will. So the flame rod is a piece of steel. You can clean it as long as the ceramic is not cracked. The flame rod is fine. If you have a one in your truck that's straight and the one from the job is the same exact thing, but it's got a 90-degree bend in it, you can bend it. All right. It's a piece of steel called NVAR, in case you're wondering. Nobody knows that but me, just because I read stupid things. And then I remember goofy things. But it's a piece of steel. Cleaning it, now the best way to clean it is actually a piece of paper. If you use too rough a sandpaper, there's some belief that you create gouges that'll hold the dirt next time and get it dirtier faster. But basically cleaning it, make sure the ceramic is not cracked. That's pretty much all there is to a flame rod. Now, a flame signal. A microamp is a millionth of an amp. All right. Now, amperage measures current flow, right? Which is current flow per current being used, whatever you want to call it. So what happens is we send an electrical current down this flame rod. The flame picks it up and carries it to ground. It's very high resistance, but a flame is a conductor. So we've got a very high resistance short. But for, what we have. And it's in microamps, millionths of an amp. So just about everybody's meter does this nowadays. We used to have special meters. So we're going to unplug the wire from the flame sensor, plug it into one side of your meter, plug the other side of the meter into the flame sensing wire, fire the furnace up or the unit up. 0.5, it will drop out. So if I do not have a 0.5 flame signal, then that's why it's locking out. If it's higher than 0.5, then it shouldn't be locking out. Then we might look at the board, might look at the wire. So this is a very simple test to do, yet I get calls all the time. Well, the flame won't stay lit. It lights, it goes out. Well, what flame signal? This is really simple to check. You put your meter in series, you check your microamps, 0.5 or higher. 3 is pretty typical. And this is pretty much the same on anybody's. Now, again, rust across this will lock this out. Okay, it has to be a flame. That's why it's called flame rectification. Rectify means convert from AC to DC. So we're only taking half the sine wave and sending it and passing it through the flame. So when we send the power from the flame rod to ground, the whole thing passes. But as power reverses and it goes from the ground to the flame rod doesn't catch most of it. So we basically catch half the sine wave or a DC voltage. So if you put a screwdriver from here to ground, it'll lock it out because it knows it's a short. Okay. Faulty pressure switch. That's pretty self-explanatory, but the pressure switch has to be closed before it's open. So if you are trying to jump out the pressure switch and then the inducer comes on, if the pressure switch is closed before the call, we're going to fault out. That's what this fault means. That's one of the things this fault means. So again, if I'm thinking the pressure switch is bad, I can just jump it out. Well, it won't work because if the switch is closed before the heating cycle starts, it'll trip, it'll lock out. All right. So if the pressure switch does not close within 5 minutes of the inducer coming on, we'll fault out. Or if the pressure switch is closed when it should be open. Okay, it will try while heating call is present, so it'll continuously retry, it won't lock out. Pressure switch must be open at the beginning of each heating cycle. So again, if you're trying to test it and you jump it out, you got to wait till the inducer comes on before you jump it out because it knows the difference. All right. Hall effect sensor. Now, I'd like to go through this a little bit more than we're going to because, but we have a limited time today. However, after the class, you're going to get some support material from this training, including this presentation, but you're also going to get a single page on testing this Hall effect sensor. This is really pretty easy. Now, the Hall effect sensor is basically a generator. If you look at an older Bryant carrier rooftop unit, say 20 years back, well, maybe not 20, but yeah, back a ways. There's 3 wires, black, white, and red coming off the back of the inducer. And there's actually a sensor in there, and there's a magnet that spins, and it actually measures motor speed. It's not a switch, it's a sensor. It generates a DC voltage, sends it back to the board to tell the board that yes, indeed, the inducer is not just running, but it's running at the proper speed. All right, so this is how we would test it. Again, you're going to get this on a paper form because there still are a bunch of the Hall effect sensors out there. All right, it is not a switch. So when you see the 3 wires coming off the back of the inducer, that's a Hall effect sensor. All right, and it generates, if you look through here, place the black test lead on pin 3 and the red lead on pin 2, slowly rotate the motor. You should get like 1 volt DC. So it's a pretty simple test. Power applied, no call for heat. Power applied, no call for heat. And then the second half of the test. All right, so it is just, again, instead of a pressure switch telling it it's on and off, it's generating a DC voltage and it's telling the board that yes, the motor's running. One of the downsides on that is if the blower wheel the inducer wheel rusted out and fell apart, and I've seen it happen a bunch of times, it didn't measure airflow, it measured the motor. So you'd come up on one and the blower motor, the inducer wheel rusted out, yet the motor was running, so it sensed it, so it tried to fire. Usually went on its limit. Okay, fault code 7, rollout switch. If the rollout switch opens, the inducer motor will be energized, the blower motor will come on, gas valve will de-energize. Air can only be reset by recycling 24 volts. So I have to kill power to the unit to recycle. Check draft inducer. So rollout switch, a couple of things. Like I just said, the draft inducer is plugged. Somebody put the wrong size wheel on there. That happens. That wheel blew apart, and it's a Hall effect sensor, so it still keeps running. Cracked heat exchangers. Prevailing wind. Sometimes the unit's situated in a way that the prevailing wind is actually blowing the burners back out of the heat exchangers. And again, check draft inducer. Fault 8, internal control fault. IGC has detected an internal hardware or software fault. Control locks out. If fault is not clear, reset or replace the IGC. If you get this fault, you probably have a low voltage short. All right, every time I've dealt with this one, it's been a low voltage short. And I'll ask you, double check all your low voltage wiring to your gas valve. This is normally what happens. You get the common reverse between the high and low stages of the valve. So you've got a short. So we're going to have an 8 fault because it sees the short. So this is typically a short on the low voltage side. The gas valve is bad, or the gas valve is miswired. So again, the most common times I run into this. So easiest thing to do with this is just start on unplugging your loads from this. So your gas valve, your pressure switch, and see if it goes away. All right, but it's either most likely it's a miswired gas valve or a bad gas valve. You got a shorted coil in the gas valve. 9, there's a problem internally, cycle power. If it doesn't clear, the IGC is bad. All right, so that's pretty straightforward. So most of these are pretty, cut and dry. The big ones, limit trip, limit trip, limit trip. We talked quite a bit about limit trips and some of the things we need to look at. Airflow is huge, huge, huge. Static is set properly. Ductwork is right. Temperature rise, easiest, simplest test, temperature rise. If our temperature rise is too high, we need to correct it. All right, there's just no 2 ways about it. That's why we're tripping limit. And if the limit trips once, and it's funny, you be standing at a parts counter, guy, well, I changed the limit and it still trips. So he's changing it again. One bad limit off the shelf, not likely, but maybe. But 2, no. If you change a limit and it's tripping again, the limit is not the problem. We need to address the problem. Start with temperature rise. You're probably going to find that it's too high. Then why is it too high? Airflow, overfired, or stratification, too high return air temperature. Those are the big three things that are going to cause it. Okay, burner alignment. Now, this is a problem we see, and it's pretty simple. Here you can see is a burner, and you see this little bar down here. Hopefully you can see here where my little laser pointer is. That little foot should be down on the bottom of the unit. Now what happens is, up here when the gas valve is attached to that manifold, and the pipe fitters hook their pipes up to that, and they don't use a backup wrench, and you tweak this a little bit, you bend this whole assembly, and you can see this bar here. This can actually get bent. So now the burners are shooting up slightly or shooting down slightly. Okay, you got to use a backup wrench on that manifold. All right, yes, there's one of those square metal plates that holds the gas valve, but we can still tweak it. But what's even worse is when you've got your piping all together and your union is a little bit short to get to, and you force it and you bend this thing up. I've actually seen this little foot where I can stick my finger on it. It's twisted, it's torqued up so high. All right, so you want to be careful of that. The alignment of these burners is everything. Right here, you can see there's no impingement. You'll see this impingement start here to where this is rusting here, or you can see the burners were hitting off that target. All right, that's definitely a burner alignment. So that's something we need to address if you see it. And again, when you're piping it, that's what causes the problem. We put too much pressure on that gas piping, and we bend the valve up or down. We bend the burners up or down. So there shouldn't be any torque on that gas pipe at all. All right. So, doggone it, so I keep hitting my mic cord here, on my headphone cord. Anyways, the cooling cycle we're going to jump into now. So a few things I want to talk about now. The small Axion units are all single stage cooling except for the 6-ton, which does use the 2-speed scroll. And some of the smaller big units use the 2-speed scroll. Now we're going to talk about this for a second. It's actually not 2-speed. The scroll plates have a couple of bleed holes in them. So what happens is when we're unloaded, we used to call them unloaders on big semi-hermetics, but what happens is we bypass some of the suction and hot gas, so we're not pumping as much. So that on the low stage, we're only pumping 67%. So if we have, like, say, a 10-ton compressor, I'm only pumping about 7 tons, a little bit less than 7 tons, 67%, because we're bypassing some of the gas going through the compressor. And we do that with these 2 little bleed holes. So you can see the little bleed ports here. So what happens is when those bleed ports are open, we're bypassing some of the gas from suction discharge. We energize this solenoid, and it closes these ports. So on your high stage, we're going to energize this solenoid. This is internal in the compressor, so if that solenoid fails, we cannot replace it. Easiest way to test that is put it on high stage, second stage, and then unplug that valve, and you should hear the compressor. You should hear it actually engaging and disengaging. So again, all that does is open the bleed port. There's one here, and it allows gas from this side to dump back into the suction side. So we're unloading it, if you will. Again, the solenoid energizes to close it. Easiest thing to do is unplug, put it in second stage cooling, unplug the solenoid, and see if you definitely hear change in sound of the compressor. You can put your amp meter on it. You'll see the amperage change. All right, the bigger units, once we get above, I think it's 7.5, we're going to jump up to the big, to 2 separate single speed scrolls. All right, first stage will always be the lower one. Okay. So on the evaporator, first stage will always be the lower one. Now that's important that we keep an eye on that too, because if stages get screwed up, the condenser fans are connected to stage 1. And so I've had this where guys swap stages and now the condenser fans don't come on because they did some wiring change and second stage comes on before first stage. So the bottom one is always going to be first stage. So that's just the easiest way to tell when you're looking at these two compressors, which one is which. Well, first stage is whatever hooked to this one. You can look at the evaporator same way. The bottom will be first stage. All right, some application notes. And now that we're using these things more and more, I mean, let's face it, every one of you either has or will work on a grow room. All right, since we legalized cannabis in Michigan, we do lots of grow rooms, which has been great for business. Nobody's going to lie about that. But we want to be careful that the equipment we're going to put in a grow facility is capable of working. Now, if you haven't done a grow facility, you may have a very small space with a huge amount of air conditioning on it. I had one I worked on. It's a 24 by 24 room, and you got 5 tons of cooling in it. Or more. I've been in spaces that aren't that big that would normally be a 5-ton load and you got 30 tons of cooling in it to accommodate all the heat lights. So low ambient accessory kits for rooftop units. A rooftop unit out of the box is designed to run down to 40 degrees Fahrenheit. All right. If you do nothing to it, it will run down to about 40 outside. Now the grow rooms will require air conditioning year round. So we need to look at the proper low ambient accessories. So the Motor Master here, which is a fan speed control, it's a condenser fan speed control, really simple to put in, and they run on condenser temperature, not pressure, but temperature. But you also need this winter start kit. All right, and we'll see this a little further on. The winter start kit, what that does is when you start a unit, an air conditioner in the middle of winter, until you build head pressure, our suction pressure is going to be really low because we don't have a pressure drop across our metering device. So we're not flowing through there, so suction pressure is low. So what the winter start kit does is it's basically a time delay that bypasses the low pressure switch for 3 minutes to allow the head pressure to build up, because the head pressure starts the pressure drop into the low side. We start to flow refrigerant and our suction pressure comes up. So that's the winter start kit's good down to 25. The Motor Master's down to minus 20, but we also need the winter start kit. So if you're doing low ambient on rooftop units, if you're doing Motor Masters, you have to use the winter start kit or you're going to short cycle. Mixed air. These units are not designed as makeup airs. They've been installed this way forever, and you get all kind of problems with them. So the aluminized heat exchangers, which is the most common, are good for 50-degree return air. All right. The stainless steel heat exchangers are only good for 40. So what I mean by makeup air, you work on a makeup air unit, it's 100% outside air. These units are not designed for that. And if you do use them for that, you're going to have all kind of problems with condensation, cracking heat exchangers. They're not built for that. They're not makeup air units. And guys like to do it because it's a cheap alternative to a makeup air unit. So they're not designed for that. So we don't want to do that. Okay, economizers. We're going to take a quick look at economizers and this new Jade controller here. If you haven't worked with it yet, they're really simple once you dive into them. But we're going to spend a couple minutes on this Jade control. So economizer is pretty straightforward. Here's my rooftop unit. Instead of my return air going across my evaporators, my compressor's running. If the outdoor conditions allow, meaning the temperature outside and humidity is lower than inside, the compressor will lock out. These return air dampers will close. At the same time, these outdoor ampers will open. The fresh outdoor air will go down into the building. Okay, that's what economizer does. Now, on a 2-stage unit, if the outdoor air conditions are better than indoor air conditions, and we open the economizer and we still don't cool enough, we can actually bring the mechanical cooling on with the economizer. All right, so we're going to dive into that a little bit. So The new Jade controller, now, and you guys have only been around a couple years, this is probably all you've seen so far, but there was some older style, prior to the 7220 Jade. All right, the 7212, which you see on the top here, this is the old economizer controller. It plugged into the motor. These are the sensors for it. First thing, excuse me, these sensors are not compatible. So as they phased this 7212 out, eventually we'll be switching to the Jade. If we're switching over to the Jade, we have to switch all the sensors as well to the Jade sensors. The damper motors are backward compatible. So whether you have the old 7215 or the newer direct drive actuators, they are compatible with the Jade. All right. If you do a Google search or get a hold of me, this is a wire for wire swap. So if I have a 7212 and I need to switch it to the 7220, why? Because the 7212 has been discontinued. This is a wire for wire swap from the 7212 to the 7220. Again, you have to change the sensors. So, economizer function. Again, if outdoor ambient. Now, first of all, let's take a look at the sensor. In Michigan, we use an enthalpy sensor, not dry bulb. So this will be an enthalpy with this temperature and humidity. So if it's 80 degrees in the building and it's 70 outside and really low humidity, I can cool with that air, right? So this thing says I need a call for cooling. It tells the unit, keep the compressors off, open the outside air damper, close the return air damper. So now I want to take that cold outside air, dump it into the space to cool it. It's great if it's 70. What if it's today? What if you turn this air conditioner on today? It says, hey, it's 16 degrees outside. We can cool with this all day. So I open these dampers and that cold air starts coming in and it dumps down the supply, 16 degree air. What happens when somebody's sitting under that diffuser at their desk, 16 degree air dumping in? It's not comfortable. So now we have a mixed air sensor right here. So what's going to happen is that mixed air sensor is going to modulate these dampers to keep this mixed air from getting below 55 degrees. All right. And it'll modulate until we cool the space, then these dampers close. The barometric relief is because we're dumping air into the building. We're going to pressurize the building. We have to let it out. It could be a damper, or on big units, it could be a fan. If it gets too hot and too humid outside for air conditioning, then the compressors will come on, these dampers will close, return will open, and it will do normal mechanical cooling. If we have a two-stage unit, let's say it's 65 outside, low humidity, we're going to economize because it's 80 inside, and we're bringing cold air in, and our thermostat calls for second stage cooling. Then with the economizer open, it will bring the first stage compressor on. Okay, so always use a two-stage thermostat when using an economizer. Even on a 3-ton unit, if you got an economizer, use a two-stage stat so that you can bring second stage cooling in with the economizer if you need to. All right, so here's the base economizer. There's the Jade module, our actuator, our mixed air sensor, 55 degrees by the blower. Outdoor air, again, in Michigan, we're always going to use the enthalpy sensor, not dry bulb. CO2 sensor, which is an option, much less used, and that's for fresh air. So again, how this is going to work. I get a call for first stage cooling. It goes to the Jade controller. The Jade says, hey, Mr. Enthalpy sensor, is it cool enough outside for outside air? Yes. Damper's open, compressor's locked out. No, damper closed, first stage compressor comes on. All right. So we call for cooling. It's the module says yes, enthalpy's low enough, we can cool, damper's open. Second stage calls, and it's going to bring on the first stage compressor. So now I can actually have the economizer with the compressor, which is the most efficient way to do it. So always, 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 always use a 2-stage thermostat when putting an economizer in. All right. So this is how it works. Now, first of all, here's your thermostat. So here's your Y1 goes to the economizer control. Y2 goes to the economizer control. Y2 out, Y1 out, actually come out of the economizer control to the contactors. So what happens if I have first stage call for cooling, it goes to the module, and if the module thinks we can cool with outside air, it locks the compressor out and opens the damper. If then second stage calls, then the module will send the call to the first stage compressor. All right, pretty simple. Now over here, I want to point something out. See, this is a, no, down here, I'm sorry. These outside air, this is the one that causes people lots of grief. Okay, these are enthalpy sensors. Enthalpy is temperature and humidity together. So if I look, the enthalpy sensors are tied into this S bus. That's Silk bus, that's Honeywell's name for this. And up here, see the outdoor air temperature terminals? There's nothing connected. That's for dry bulb. Dry bulb is strictly temperature. If you're putting an economizer on in Michigan, we don't even bother with dry bulb. Because if it's above 60 outside, you can't economize with dry bulb. But what guys see is they install one of these and say, well, I don't have an outdoor air temperature sensor. So they take the wires off of here and connect it here, and then they call me because they're getting a fault. All right. So the enthalpy sensors are tied in to the S bus, not the outdoor air temperature sensors. Okay, so and then there's a mixed air sensor, which is mixed MAT. And then aux2, I want to talk about this for a minute. aux2, which goes to, where is it at? Yeah, our heating stage actually, oh, they don't show it here, but our heating stage actually, when we call for heat, we're actually going to send an output to the economizer module because these, remember the 2-stage blowers? So that we can bring on the second stage blower minimum position, and we'll talk about that in a second. All right, at this link right here, this www.youtube.com, there is a video installing this micrometal economizer with the Jade control with setup. If we were sitting in a classroom together, I would play this for you, but because my bandwidth and your bandwidth are not big enough, I cannot run it right now. But if you go to Micrometal's website, you can look at this video, so it's definitely worth watching. So again, here's that enthalpy sensor. This is inside the return air hood. That's the outdoor air damper right there. See the gray wires here? Those gray wires plug in here. Let's see the gray wires. This purple and pink are for the dry bulb sensor that we're not using. So again, these purple and pink, we don't even use those. It's the gray wires that go to that silk bus. All right, the vane axle. This is the 3 to 6 ton with that direct drive blue fan. All right, now if we look at these two terminal boards, your economizer control is going to plug in right here. See that there? Now that plug is different than this plug on the smaller units. The economizer control is designed to plug into this. So with your paperwork, with your Axion, you're going to also receive these two harnesses. Okay, when you see these two harnesses, leave them with the unit. If you're not putting an economizer in, leave them with the unit. If you are going to put the economizer in, you have to have these two plugs to adapt the economizer plug from this to this. All right. So you have to have those. So when you see these two jumpers shipped with the small unit, you have to keep them with the unit, even if you're not going to put the economizer in today. All right. One other thing I want to point out. This plug right here. Now, this is where the economizer plugs in. If you've ever put an economizer in, you put the economizer in the unit. This is the return section. There's a jumper plug shipped from the factory attached to this little 12 pin. You have to unplug the jumper to plug the economizer in. Take yourself a tie wrap or wire tie, whatever you want to call it, and tie that jumper right here. Because if your economizer ever fails, we can simply unplug it and plug the jumper back in. Okay, because remember, the economizer controller locks compressors out. So do yourself a favor and keep that jumper with this plug. All right, and leave these jumpers with the unit if you're not putting an economizer in. If you are putting an economizer in, you're gonna have to use them. So when you go to plug your economizer in and it doesn't work, the plugs are different, you need these jumpers that are shipped with the unit. If not, there is the part numbers. Okay, enthalpy settings. Now I'm going to talk about this for a minute. And a lot of guys out there go, oh, enthalpy sucks and enthalpy sensors suck and I hate enthalpy, and we always put it on D, right? If you worked on the old 7212 or even the predecessors going back to the old gray metal box with a big knob on it, we had settings A, B, C, D, and those were enthalpy. Now you look on the psychometrics chart, and enthalpy is a combination of temperature and humidity, or total heat content. So it means at higher temperatures, I have to have lower humidity. At lower temperatures, I have to, I can have higher humidity. So it's looking at a combination. So we always set everything to D in the old school economizers. Now this is a little different now because we're no longer looking at enthalpy. We are now looking at temperature and humidity separately. The factory default of that control is the ES3. We don't have A, B, C, D, E anymore. So ES3 is enthalpy setting 3 is the default, and it actually is a range. See, instead of one single point, it's a range. So dry bulb temp 70, dew point 54. Okay, enthalpy total 24 pounds a day. So that's where it's set at. And what it will do is 0.1, the low point, at 70 degrees outside air with only 42% humidity, we will economize. Anything below 42. So 70 degrees outside, wow, that seems awfully high, right? Well, if the humidity is only 42%, we can cool with that. Now, it has to go all the way down to 60 degrees if the humidity is over 80%. Okay, so you can kind of see where the two come together. Now, normally we can leave that default alone, all right? Again, the beauty, that's why you always want to use a two-stage thermostat, because in the event the economizer is open, because 70 degrees, 42% humidity, and for some reason we still can't cool the space, we are still going to allow the compressor to come on, even on a single stage unit. So you normally shouldn't have to change this setting. That's the factory default. Mixed air. Now I hear guys say, well, you don't really have time to do this. Well, the proper way to set mixed air is this. If you look at a damper and you say, well, I'm going to set mixed air, or minimum position air, because by code, we have to allow so much circulation air in. So we set the dampers to never closed or unoccupied. They're going to be open in minimum position. And if you set the damper at 10% physically, you got about 30, 35% airflow. They're not linear. So 10% of damper opening does not give you 10% of airflow. So, and then we have on a 2-speed blower, we're going to have high-speed blower position minimum, low-speed blower minimum. So you'd have to do this on both. Now, the correct way to set, and there's a couple ways, but this is the way I always did it. How much fresh air do I need? Well, that's easy. What by code is the space you're using? It's a movie theater. How many CFM do I need per person? All right. Now, my rooftop unit is a 10-ton. How many CFM is that? Anybody? So 400 CFM per ton, so that's 4,000 CFM. So what's 10% of that? Okay, that's how I'm going to figure out what is my fresh air percentage and how many percent of that is it? So, so we figured out we need 10% fresh air, right? So in our particular installation, we need 10% of fresh air. Outdoor air is 60, return air is 75. Okay. So what that means is if I need 10% outdoor air, 10% of 60-degree air, then I need 90% of 75-degree air. So return air is 75, outdoors, so 60 outdoor air temperature times 0.1, 10% is 6. 75 return temperature times 0.9 or 90% is 67.5. So add the two together, my mixed air temperature, 73.5. That is the temperature I should have in mixed air when my minimum position damper is set properly. Like I say, well, who's really going to do this? Well, this is how you actually do it. Now, I know a lot of guys leave it at the factory defaults. That is not correct. So I calculate this out. I put my probe in my mixed air by my blower, and I'm going to adjust my minimum position until I have 73.5 in this example. All right. Now, if I have a 2-stage blower, I'm going to have to run high speed and set it and low speed and set it. Okay, because they're different. And what you're going to find is that at low speed, the blower is actually going to be further open physically than on high speed. Okay, now the Jade setup. So put the economizer in. On the aftermarket, sometimes these aren't set up, or if I have to replace this module. First of all, the Jade module is really cool. And if you get a chance, if you Google, not Bing, that you got to go to Google. Google knows everything. Google Honeywell Jade simulator. And it'll take you to a little Jade looking control, which is interactive and allow you to go through all this stuff. You can force dampers open, turn compressors on. You can see what your enthalpy sensor is. You can see what your outdoor temperature is, your damper position. You can drive your damper. So it's really a great control to work with. But when I get one, we have to set it up. And this is the call we always get on these. So we're going to take a look at this. This is pretty simple. We got set points and system setup. So mixed air temp. Remember, that's what controls outdoor air dampers so we don't get too cold into space. So my mixed air temperature, factory default is 53 degrees. Excuse me, I can change that. Why would I want to change that? Well, maybe this is a factory. I don't care if the mixed air is colder. And I got a little heavier load, so I want a little colder air coming in. Well, great. Then we can change it from 38 to 70. I can change my mixed air. All right. Low temp lockout, factory default, 32 degrees. What this is, if it's less than 32 outside, this will lock the compressor out. Well, I know before long we'll be out doing AC checks because business is going to slow down and our bosses want to get us out there making money again, right? So you're brushing snow off the top of a rooftop unit to do a maintenance, and you're supposed to check the air conditioning. Oh, it's 30 degrees outside. The economizer's locked out. I've got the compressors locked out. I can actually go in there and lower that so I can get the compressors to come on. Or again, you're in a spot where it's an IT room. I want the compressors to come on if we need them, so we can lower that. Dry bulb setting. If you're doing an economizer in Michigan, don't use dry bulb. That's an outside temperature sensor, not enthalpy. Don't even bother. Enthalpy curve, again, that's that chart we looked at, ES3. You probably should never have to adjust this because it does cover that whole range. So you, like we used to have to go to ABCD, you shouldn't adjust this. Minimum position. Now on a single stage unit, I have a single minimum position. Now this is a 2 to 10 signal going to this damper motor. So 2.8 volts DC, that's the signal it's sending out. That's the factory set minimum position, but it's a 2 to 10 volt signal. And we talked about using a temperature probe to correctly set our mixed air. Now, if I have a 2-speed blower, I'm going to have minimum position high, minimum position low. High is 2.8, low is 3.2. Because again, low, the damper is going to be further open. A lot of guys leave it at this. It's not correct, but it'll work. Okay, so most of this factory settings, it'll work great. You'll never have to mess with it. But let's go down to system setup. you have to do the system install. That's just a date, which is, you can look back on when you put it in. Equipment type, conventional. Even on a heat pump, it's going to be conventional on equipment type. aux2 in, W1. Why on earth is the W1 going to go to the economizer control? Because W1 is high speed blower, right? And if we've got G energized for circulation, we're on low speed blower. So when we flip to high speed for the heat, I need to make sure my damper adjusts to the high speed damper because it's not as far open. So that's why W1 is actually going to send a signal to the economizer control. Fan type, this is where this would be set up for 2-speed fan or single speed. So look at default is 2-speed. You're putting it on an older single speed. We got to get in there and change that. Aux out 1. That is a alarm that we're going to end up using in the future, as California does, as the rest of us do. California currently, if your economizer faults, we have to get an alarm back down to the thermostat. So that's what this is monitoring. So in the future, we'll have to put aux out 1 to system, and we're going to have a thermostat that actually has an economizer alarm on it. So that if I have an economizer fault, the user gets a notification. Then occupancy input, we're going to leave that alone. So these are pretty cool to set up, pretty simple to set up. Some of the biggest things I've seen an issue is this low temp lockout is set too high and the compressors won't come on. That's been a big one, or this mixed air is jacked up. Okay, there's some settings in there for airflow, CFM. We're not using any of that, so don't mess with any of that. This is all you have to mess with the Jade. Again, some of the support material you'll be receiving by email will include the setup instructions and things like that. So transformer primary. I can't tell you how many times on job sites we go out and we find this, and something so simple can cause all kind of problems. We have 208, we have 230. All right, we have I think guys are used to motors being multi-voltage. Transformers are, but you have to wire them accordingly. If you have 208, meaning you check the primary voltage, it's 208 volts. I have to set the taps on the transformer for 208. If I have 208 and I have the transformer set up for 230, I'm going to have low secondary voltage. I might have 22 volts. And it might work sometimes. Your contactors might chatter. You might burn contactors up. So this seems like a really simple thing, but it gets mixed all the time. So first thing you should do, check your voltage. If I have 208 going to the transformer, make sure you set it up accordingly. If I have 230, make sure you set it up accordingly. What if I'm sitting at 219? Well, check it both ways. And whatever way you get the highest on the secondary side, that's where we should be. Now, I don't mean, it's 208, so set it for 230, because then we're going to be too high. But if you're not sure, 219 is in between. Which one do I use? We want to, we should have 227, 26, 27 volts on the secondary transformer. But make sure you do this. I can't tell you how many times I've been on jobs or gone to jobs and the contactors are chattering, burning contactors out, economizer issues, and it all relates to this. Okay, so voltage and current imbalance. Now this, again, like I said, used to be we checked voltage and we're good, right? We got voltage. But with all the electronics, VFD, ECM motors, economizer modules, voltage imbalance is going to locks things out now. If we have a bad voltage imbalance, the VFD can lock itself out. That ECM can lock itself out. So this is really, really critical to check our voltage imbalance and our amperage imbalance. All right, because if it's outside of allowable specs, we're going to have problems. We're going to have faults. And our whole goal here is to not ever come back, start it up, come back for maintenance, but I don't want other issues. So check your voltage imbalance. Check your amperage imbalance. Factories, a lot of times we have, especially with a wild leg, we'll have an amperage imbalance because there's more loads on the 110 legs than there are the 208 legs. Because all your lighting's on your 110, nothing's on your 208. So check those. High and low voltage. This is another one I can't stress enough. Check your voltage. If you got 250 volts, you need to put some, or 248 even, you need to start putting some voltage protection on these things. If you get 255, your voltage is high. Something needs to be done with it. Well, the old equipment, I know what old equipment used to do. The compressor would run on whatever you gave it. Well, we're going to have more and more electronics hitting this equipment. And it's not just ours. So how high the voltage is just as important as voltage imbalance anymore. If the voltage is too high, we got to do something with it. It'll lock those motors out. And if we're sitting right at the limit, you're going to have sporadic problems where you're locking motors out. It needs to be addressed. Again, with the VFDs or the ECM motors. So get used to checking that, surge protectors, phase monitors. But, again, there's power to these drives all the time. So we might have to add a contactor through there. These startup check sheets. Now, I've been doing this training now for this particular rooftop unit, I think for a little over 3 years. And at the end of every class, I tell the guys, hey, these checklists come with the rooftop units. And as someone working at a company or a business owner, or this is a great startup document that not only walks you through all the procedures you're supposed to be following, but you also have a great document at the end that you can keep in the files. I used to do this on all my jobs. I suggest you do them on all the jobs or the jobs the guys are doing for you, because there's your voltage. You're going to check your imbalances. It's going to walk you through your compressor setups. So this is just a great, simple check sheet. Like I said, it comes with the units. Take the time and do it, because I know our goal is to get the install done and not have to come back. Check the gas pressure, not just assume. The belt and static, those are two huge things that way too often get overlooked. And too many of our phone calls are tied to those. Temperature rise and cooling temperature split. Setting the economizers up properly. This is going to walk you through all that. Again, most of the calls we get, a lot of the calls we get are related to things that should have been handled as setup. I know I've talked about belts a bunch of times, but that's really one we get a lot of calls on. So I really suggest that you use these check sheets, these startup sheets, and keep them in records. So that being said, the support material that I talked about, the economizer setup and things like that, will be sent to you after this. Where we go here. So if that's all I have now. One thing I'm going to add here. I am going to put my email address here, because I know what happens is you're sitting in training and you think about a half hour from now, a question you wanted to ask. So what I just added on here, I show from Gurn. That is my email address. Feel free to contact me if you have questions later on. Okay.
Also, sorry. Yeah. I was going to say, do you mind going back to that slide that had the URL for that YouTube video that you mentioned, that walkthrough?
Oh, no, I can do that.
Because I'd like to send that to someone. Asked to put it in the chat.
All right, there we go. So there it is.
Perfect.
This is a great video. I unfortunately in this format I can't show it. It won't come through because.
Can you? Yeah. Can you copy and paste it into the chat, or no? Are you on the edit of the? Doesn't look like it.
Yeah, like I'll see. Let me see if I can do that.
And that was the last question that someone asked, was just doing that.
Copy. Shoot. the heck did my chat box go? There it is. Everyone. Yeah, it didn't
Didn't send. Let me quick.
try it again here. Copy. Oh, there it goes. All right. So I just put it in the chat.
Yep. Perfect. I'm gonna copy and paste it, and I'm gonna include that in my email as well to everyone.
So
Awesome. That's everything then in terms of the chat. Yeah.
All right. Now, also, everybody, well, thank you for tuning in today. But what I also would like to ask is Isaac is going to send a critique to you. And I know everybody hates doing critiques. I'm the worst for it. But I'm really going to ask that you do. This format is still really new to us, and we're trying to give you the best training we can. So those critiques really help us in what we're doing. So please, if you could, when you receive it, take a few minutes and fill out the critique. Like I said, it just helps us, improve what we're doing. So, please and thank you. I ask that you fill those out.
Awesome. Hey, thanks so much, Dave. I appreciate it. And
all right, Isaac, thank you.
Commented thank you as the usual.
Oh wait, somebody. Oh, okay. All right, well, good. Well, somebody just put a chat in there. Thank you very much for your kind words. All right, well, that's all I have for you. Go out and shovel. I don't know about where you guys are at, but where I'm at, we have a lot of snow.
For sure. Hey, thank you so much, everyone, for attending, and thank you, Dave, and everyone have a great rest of your day.
All right, thanks.